The cylindrical coordinate system is basically an extension of the polar coordinate system. There is no two-dimensional analog for spherical coordinates. It's an entirely new coordinate system. It still references points in R3. So we still have in the spherical coordinate system the x-axis, the y-axis, and the z-axis oriented the way you expect. What's different is how we reference a point in the spherical coordinate system. Let's say we have a point P in space. In the rectangular coordinate system, it's going to have coordinates x, y, z. In the cylindrical coordinate system, we're concerned with r, the distance that the projection of the point in the xy plane is from the origin, and the angle made in the xy plane with the positive x-axis, theta. Z is, of course, what we expect it to be, and we end up with a representation of a point in the cylindrical coordinate system, r theta z. For the spherical coordinate system, we do keep the angle theta, where that's going to be one of our coordinates, but we are interested with the distance that a point is from the origin. That distance is denoted rho. It's a Greek letter. We've seen it before in the context of density. It has nothing to do with density here. It's the Greek letter r and its radius, essentially. In addition to being concerned with rho, I got ahead of myself, we are concerned also with an angle phi. That angle is made with the positive z-axis. And a point in spherical coordinates has coordinates rho, theta, and phi, where again, rho is the distance from the origin to the point. Theta is the angle between the positive x-axis and the projection of the point in the xy plane. So theta lives in the xy plane. And then phi is an angle made with the positive z-axis. The spherical coordinate system tends to be useful for cones and spheres. Got to be careful with the spheres though. Sometimes cylindrical coordinates are indicated. It really depends on the trace in the xy plane. But a lot of times when you see spheres, you're going to go spherical coordinates. They're named spherical coordinates for a reason. Now let's look at our conversion factors, and for that I'm going to reproduce a chunk of this picture here. Actually, I decided it'd be useful to reproduce the whole thing. All right, what we're after now is expressions for x, y, and z that involve rho, theta, and phi. I've put down against the xy plane a right triangle so that the triangle formed by the segment that I labeled rho and the segment in the xy plane that I labeled r, and that vertical that gives us the projection of P onto the xy plane forms a right triangle. Because this vertical is parallel to the z-axis, we know that the upper angle of the right triangle has a value of phi because of alternate interior angles. The vertical distance between the projection in the xy plane and the point P itself is of course z. And using right triangle trigonometry, we can say that the cosine of phi is the adjacent, which is going to be z, over the hypotenuse, which has a length of rho. So the cosine of phi is equal to z over rho. That gives us that z is equal to rho times the cosine of phi. In the same way, because the segment labeled r is opposite that phi in that triangle, we can say that the sine of phi is equal to r divided by rho, which means that r is equal to rho times the sine of phi. That's useful because x is equal to r times the cosine of theta, and y is equal to r times the sine of theta. Therefore, we can now change out r in both of those expressions. So in addition to knowing that z is rho times the cosine of phi, we now have that x is equal to rho sine of phi cosine of theta, and y is equal to rho sine of phi sine of theta by changing out r for rho sine phi. It follows then that a point that has coordinates x, y, z is equal to rho cosine theta sine phi rho sine theta sine phi, rho cosine phi. This is the order in which you typically see like the cosine theta and then the sine of phi. I know I didn't write it like that initially when we did the substitution just now, but this is typically what we see. Here's what I remember. Rho is going to be associated with x, y, and z, right? And we know that from cylindrical coordinates, x is associated with the cosine of theta and y is associated with the sine of theta. Somehow I need you to work on remembering that for x, you have a mix of cosine theta and sine phi. Then that might help you remember that for y, it's the sine theta and sine phi, but really where it's different is that z uses the angle phi, but it's the cosine. And maybe a way to remember that is to remember that in this triangle that we developed, we were working with phi was the upper angle, and we're probably used to working with a lower angle in a right triangle situation. And so where I might want z to be the sine of phi, maybe I can remember, well, no, we developed it differently, so it's the cosine of phi. But I really think the way to remember this is to remember that x is cosine theta sine phi, and then try to remember how y and z are different. Now, because rho is a distance, no, I have a label here that I think may be confusing. P here is the point P in space, right? Rho is the distance from the origin. Now, because rho is the distance from the origin, we have that x squared plus y squared plus z squared is equal to rho squared. If you're thinking that that looks like the equation of a sphere of radius rho, you're exactly right. In fact, if we had, say, x squared plus y squared plus z squared equals 25, that would translate to rho equals 5. Folks, these are both ways to express a sphere of radius 5, and you can see why spherical coordinates have their name. It's really easy to represent a sphere in these coordinates.